Toronto, and she's going to talk about Poisson maps between character varieties.
Except, let's see, how do I, oh, okay, good. Yeah, so this is joint work with Indranil Biswas, Jacques Rutevis, and Sean Lawton, and our paper will be published in Journal Symplectic Geometry. Okay, so this was the rough plan. Talk about Poisson structures, maps between surfaces, and construction of Poisson structures, and finally capping and gluing operations. So if you have two surfaces, possibly surfaces with boundary, let's let G be a reductive Lie group, or includes a compact, could be a compact Lie group. And I will let X of sigma be representations of the fundamental group of sigma into the group G up to conjugation. So this for sigma 1 and sigma 2. Here, Gx by conjugation. These spaces are Poisson manifolds. If the boundary of the surface is empty, then they are symplectic. So one map that we will consider is the inclusion map from, we could consider sigma 1 as a submanifold of the surface sigma 2, and F is just the inclusion map. Then we get a morphism from X of sigma 2 to X of sigma 1. So strictly speaking, we will think of maps up to, these are maps in the spaces of representations, but because the map is equivariant with respect to conjugation, the construction descends to the character variety, which is the space of conjugacy classes of representations. Sometimes we'll denote a surface of genus G with n boundary components as sigma sub n comma G. And then X of sigma n comma G is being denoted X of n comma G. We will show that the map phi is Poisson, and we will generalize it from just the inclusion map to other maps of surfaces. So if there are any questions or questions in the chat, please tell me. We will usually use coordinates that come from loops in the surface, and Zi will correspond to the trace of the representation around the loop. And then the Poisson phi vector on the character variety is written. The Aij are usually polynomials in the Zi. So I should have said that Zi is just the trace of the holonomy of the representation around a base loop in the surface. The base loop gives rise to an element in the fundamental group. So typically these base loops intersect, we will require that the base loops intersect in transverse double points, and write alpha cap beta as the set of intersections. And epsilon denotes the intersection number of the loops at the base point P. Alpha sub P denotes a curve alpha based at P, and R just denotes a representation. We'll denote F sub alpha of R as the function F evaluated at the value of the representation on the loop alpha. Oops. So if A is an element in the group, we define capital F of A. This will be an element of the Lie algebra. It's just, so if X is an element also of the Lie algebra, this is just the derivative at 0 of A times exponential map of Tx. The angle bracket is just typically the killing form. It's an adjoint invariant inner product on the Lie algebra. So in the case of G equals UN or SUN, F of A is just half of A minus A inverse. It can be shown that F of A is an element of the Lie algebra of G. This definition, by the way, is due to Bill Goldman. When R is a homomorphism from pi to G, the Poisson bracket turns out to be, this is due to Bill Goldman. Turns out to be a sum over the intersection points of the loops alpha and beta, and the sum of the angle brackets of F and G, evaluated at these representation of alpha, representation of beta. So this was Goldman's characterization of the Poisson bracket on the space of representations. Oh. So if Q is a continuous map between two surfaces, you get a homomorphism of fundamental groups and a continuous map from fundamental group of sigma 2 into maps of that into G to fundamental group of sigma 1 into G. And this map descends to character varieties. This gives rise to a map, which I'll denote Q lower star, from the character variety of sigma 2 to the character variety of sigma 1. Is there a question?
There are no questions.
Hello?
There are no questions.
No questions. So Goldman showed that if Q is a map of this type, and also Goldman required that this map preserves transversality of base loops and preserves double points. In that case, the map of coordinate rings is a morphism of Poisson algebras if Q preserves orientation, and if it reverses orientations, it's an anti-Poisson morphism. The Poisson bracket on X of sigma is given by Goldman in 1986. This was in the case no boundary components and genus greater than or equal to 0. His student Adam Sikora characterized the situation in the case where G equals 1, where you have a torus with no boundary components. Sean Lawton studied the case where there are boundary components. And the case where you have a torus with a one-fold torus, a torus with one boundary component, the Poisson bivector was computed for SL2C by Goldman and for SL3C by Sean Lawton. In the case of SL2C, Goldman also found the Poisson bivector for n equals 4, four-hold sphere, and the two punctured torus. So now let us assume the surface. Let's think of an open, smooth manifold rather than a manifold with boundaries. So this corresponds to a surface with punctures instead of a surface with boundary components. We'll assume that the group G is either a compact group or a reductive group, the complexification of a compact Lie group. We fix a base point. Then a homomorphism from the fundamental group to G is called reductive if the Zariski closure of its image in G is a reductive subgroup. This condition is always satisfied if the group is compact. So we define XNG as the quotient under conjugation of the space of reductive homomorphisms of the fundamental group of a surface. And a G connection on a surface will mean a smooth principal G bundle on the surface that is equipped with a connection. If we let E be a vector bundle over the surface, let E be a vector bundle over the surface that is associated to the principal G bundle through the adjoint representation. Poincare duality tells us that the tangent space to the character variety is the compactly supported first cohomology of sigma with coefficients in E. There's a natural characterization, natural map between the cotangent bundle to the tangent bundle. Equivalently, there's a two form on the character variety. This is obtained by taking the the wedge product of a one form on the surface with would be a vector bundle valued one form. Take the wedge product of that with a compactly supported one form, and that gives you a compactly supported two form. And then that is integrated over the surface. This construction, in the case of a compact oriented surface with no boundary components, gives rise to the two form that gave the symplectic structure that was constructed by Attia and Bott, and also by Goldman. So we'll denote this by theta. This is really a two form over the surface. Suppose sigma is embedded, sigma 1 is embedded in sigma 2. Then the restriction map from sigma 2 to sigma 1 gives a map, which I'll call phi, from one character variety to the other. And we then have maps, which I'll call beta. This goes from the first cohomology in sigma 2 to the first cohomology in sigma 1. This just comes from restriction from sigma 1, from sigma 2 to sigma 1. And there's a map in the other direction, which is for compactly supported cohomology. So the map beta is the same as the map d phi, and it results from pulling back one forms under the inclusion map. The map gamma is actually the dual of the map d phi, and it results from pushing forward compactly supported forms from sigma 1 to sigma 2 under the inclusion map. So to study whether a map preserves the Poisson structure, we characterize it by seeing that a map from between two Poisson manifolds A and B is a Poisson map if and only if the differential of the map intertwines these two forms, these two forms, theta 1 and theta B, theta A and theta B. So let's let phi, little phi, be a covering map from sigma 1 to sigma 2. It could be a ramified covering map. Then define psi as a map of character varieties from sigma 2 to character variety of sigma 2 to the character variety of sigma 1. This is obtained by pushing forward the fundamental group under phi from sigma 1 to sigma 2. We show that the map psi is a Poisson map. The proof uses the fact that deep psi sends a cohomology class to its pullback under the map little phi. And the map dual to d phi sends a compactly supported one form to the sum of its pullbacks over the inverse image points under the map little phi. This form is also compactly supported. So I'll describe some morphisms of character varieties which we get by natural operations on the surfaces. One operation is by capping off boundary components. So if sigma 1 is the two manifold with boundary, let's let sigma 2 be the two manifold obtained by capping the boundary components as described below. So you take one thing you could do is cap off a boundary component just by a disk. The image is the image in the character variety is the union of a family of symplectic leaves. You could also cap off with a cylinder. So that means you glue the two boundary components of the surface like this. This produces a surface with two less boundary components, and the genus is one higher. The two character varieties have the same dimension. You could also cap off a surface with k boundary components with a k-hold sphere. So the resulting surface has k less boundary components, and the genus increases by k minus 1. In this case, the map of character varieties is not surjective. You could cap off one boundary component with a one-hold torus, like so. If the group is semi-simple, then the map phi is surjective in this case. And you could cap off with an n-punctured genus 1 curve. So I've drawn the case where you have two boundary components. In this case, the map is a Poisson map, and it is a surjective map. So I have 2 minutes left. I don't really have time to say much about the relation with Q Hamiltonian spaces, which is the work of Alexeyev, Malkin, and Meinrenken. I'll say only that these authors constructed quasi-Hamiltonian spaces, one purpose of which is symplectic quotients, or quotients of these are character varieties. And so what you can do to form a Poisson map is set the values of the moment maps corresponding to some components of the variety to be equal, and then take the quotient by the diagonal action of the group. Or similarly, if you have boundary components of two different surfaces, you just set the moment maps equal and take the quotient by the diagonal action of the group. So this produces a way of understanding the capping procedure. So I'm out of time, so I will end there. Oh, let me give you the references. So this is the paper of Alexeyev, Malkin, Meinrenken. These are the papers of Goldman, Lawton, and Sikora. So I'll end there. Thank you.
Thank you very much.
Maybe I have to stop sharing the screen so that I can see the audience.
Questions or comments? Yeah, Can you check if there is any questions on the chat?
There aren't any in the chat, as far
Okay.
as I can see.
So if there are no questions or comments, let's thank Lisa again.